Okay, so continuing on with logarithms, we skipped this section on logarithmic differentiation. Logarithmic differentiation is just a technique to use when other techniques might be a little bit complicated. You can see here in the example that if we did the quotient rule with this, not only would we have to do the quotient rule, we would have product chain into the product rule on the top. We would get another chain rule with the power rule here. And it just gets really complicated. You start adding in trig functions and all the other things as well, and it just gets really, really complicated. Logarithmic differentiation, while it's not neat, it is a different technique, and each of the steps themselves are very, very simple. And so simple yielding a complex result is sort of better in the fact that we have computers that can do the complicated calculations if we can give it the right formula. So there's a couple of things here is that this is a technique, which I misspelled. It is a technique that's used. It is not how you do the derivatives of logs. And the only restriction on it is that y has to be greater than or 0, because remember, you can only take the log of a positive number. So let's look at this example here. We're going to use logarithmic differentiation on this. At the bottom of the sheet, I did give you all the steps to take. We are going to do these steps, but I will just say them as we go. So the first thing we're going to do is we're going to take the log of both sides. This step you will probably skip in your homework, just because y'all don't like to write extra steps down. But I like to have my notes complete. So we take the log of both sides. After we take the log of both sides, we're going to expand using those properties of logs that we reviewed on the previous page. All this. So anything that's in the numerator will be added as a fact. Any of those factors will be added. Any factor in the denominator will be subtracted. And any powers on those factors will be brought down in the front. So what that means is we have the natural log of y equals, we're going to do the natural log of the first thing here, which is natural log of x squared plus 1. This exponent does not get pulled in front because it's not of the whole thing, so we're going to leave that there. This next one is in the top, so we're going to add. There's a power on this, so that's going to be 1/2 natural log of x plus 3. No more in top, so it's going to be subtraction for the rest on. This is in the bottom, so it's going to be minus natural log of x minus 1. So now we've expanded that. Yay, it looks messy now. Well, now we're going to take the derivative. If we watch when we take the derivative here, which by the way will be implicit because this is not y equals anymore, that's actually really easy to take the derivative. The derivative of natural log of y is 1 over y. Since we're doing that with respect to x, we do have a dy dx factor here, which is good because this is what we're looking for. And then the derivative of natural log of x squared plus 1 is 1 over x squared plus 1. It's 1 over the inside times the derivative of the inside, 2x. This is the chain rule. Then we have plus 1/2 times, because that's just a constant multiplier, the natural log of x plus 3. The derivative of that is 1 over the inside, 1 over x plus 3, times the chain rule, which the derivative of this is just 1. Minus, nothing in front, so it's just 1 over the inside, x minus 1, and then times chain rule of times 1, which we don't need to write. After we differentiate, we're going to solve for dy dx by multiplying by y. When I do that, I'm also going to simplify anything I can in these factors here. So I get dy dx equals y times, looking at these two factors, I get 2x over x squared plus 1. Nothing cancels there. Plus 1 over 2 times x plus 3. Remember, leave your denominators factored. Multiply out your numerators always. and then 1 over x minus 1. Okay, we're almost there. The only problem is that we have a y. If we can change that to in terms of x, we're good. Well, luckily we can, because that's what the original problem was. So dy dx equals, and then we'll write the original, x squared plus 1 times x plus 3 to the 1/2, all over x minus 1. And then we have this lovely factor here, plus 1 over 2 x plus 3. If you write 2x plus 6, that's not going to be that big of a deal, but again, I would leave them factored, just as a rule of thumb. And then we're done. You're going to stop right there. There might be a little bit, if you did a lot of math, a lot of simplifying, there might be some simplification, most likely not too much. But we have a complicated derivative, but we do have the derivative, and each step was easy. And that's the purpose of this logarithmic differentiation, is that it's an easy way to get to the derivative, even if it is a messy answer.